little bit of on the heat emission systems and the relevance that it is for high temperature and low temperature in particular heat pumps that I have in mind. So with this said, I'm going to kick off and throw into more or less a short introduction to see what are the drivers behind this. So in particular, when we look at the low temperature, low carbon technologies, and we all know that we have a massive target to achieve 51% CO2 reduction by 2030 and to become carbon neutral by 2050. We're looking at, let's say, uh, typically we are familiar or most common systems are used are the high temperature systems using fossil fuels, whether they're with gas, natural gas, LPG or oil, kerosene. I want to briefly touch on the importance of the heat pump technology and its efficiency and how we can use that in particular for domestic applications in conjunction with low temperature systems on the floor heating and low temperature radiators. And then to see how we can actually retrofit these heat pumps, in what kind of scenarios are these suitable, what can we do to uh, let's say, retrofit a heat pump if the house is not ready for that, and so on. And briefly at the end, I'll just mention on the applications where heating and cooling can be used. Most heat pumps available in the market, air source heat pumps or ground source heat pumps, uh, can do both heating and cooling. Actually, when air source heat pumps, when you go in defrost, it goes in cooling mode. So this is really just to see the main things I'll touch on, and then the agenda would be the transition from fossil fuel to renewables and how we've done that successfully over the last number of years. It is the drivers behind this. So we are governed really by EU laws, and in line with that, we are in line with the European Performance of Building Directive. From 2005, used as a benchmark, we have continuously improved in, let's say, reducing our energy consumption and the carbon emissions for dwellings and for non-dwellings, for the commercial buildings. And more recently, over the last number of years, our government has published the Climate Action Plan, revised last year, just before Christmas. And we have also in law since December last year a climate action law on this. Uh, we have then, we'll be talking briefly about the high temperature systems using boilers and radiators, and up to 15, 20 years ago, that was and still is in certain applications, the most common system that is being used. We'll be looking at low temperature systems using heat pumps on the floor heating and radiators. I'll just, this will be the most common systems and solutions that are being used. And then we'll look a bit at retrofit and at radiators. As I said, suitability to put in a heat pump in a retrofit scenario. Can we use the existing radiators or the existing cylinder, or we have to resize this? And the new trend of emitters, it's more, let's say, looking a bit at the cooling end of things. So transition from the fossil fuel to renewable drivers, as I mentioned earlier, we have Part L for dwellings, technical guidance document 2019, and technical guidance documents for building other than dwellings in 2017. Both of these have introduced what's known as a renewable energy ratio concept, which is reflected in the renewable energy that is generated, whatever the renewable source is. With in mind also, we obviously we have to reduce the energy and the CO2 emissions, which is measured in the energy performance coefficient and the carbon performance coefficient for both in deep and in NEEP. As mentioned, we have the climate action plan, which is target to reduce the 51% carbon emissions by 2030 and looking to achieve carbon neutrality by 2050. It is a big challenge, I can tell you that, because I think last year we've increased that by 5%. A very important piece that was published recently is the SEI National Heat Study, that's looking at a few scenarios, I think 5 scenarios in which we can achieve net zero by 2050. So I really recommend to look through that. It's a very good piece of work. Also, Renewable Energy Ireland has published last year a 40 by 30. Another, both of these are available in free and PDF to be downloaded. It is, as I was saying earlier, very big challenges ahead of us, and I think the solution will come from a multifaceted approach where we can reduce energy consumption, not just by using one particular technology. I'm talking this now at a bigger scale, domestic, commercial, industrial, and so on. Looking at existing, let's say, high temperature systems, existing or new, typically what we use for this is condensing boilers, which will have an efficiency of approximately 90%. And typically for this, we have them working at 75, 65. Boilers will work best in condensing mode when we deliver 45 degrees, but typically that's what's out there, 75 over 65 flow and return. Traditionally, steel panel radiators are and most popular and have been used with boilers. And radiator manufacturers will typically provide outputs for the radiators at a delta T50. Accordingly. Yeah, just a few examples. Probably most of you familiar with a radiator style with boilers that we use for domestic applications and commercial, semi-commercial. You'll have typically a wall-hung system boiler that is either in an S plan or a Y plan, and then with that we do heating and hot water. But the most common radiator is the steel panel radiator. Aluminium radiators also become very popular, but mostly to be used in conjunction with low temperature system due to their low water content. Well, explain a little bit and go a bit more detail on the delta T that is spoken a lot about it. The delta T50 is the mean radiator temperature and the difference between that and the air or the room temperature. So you will have at a delta T50 flow over return 75 over 65 degree and at a room temperature of 20. So when you do that calculation, that it's 50. 75 plus 65 divided by 2 minus 20. So similarly, if we do the mean between 45 and 40, which are the typical flow return temperature for a heat pump, air source or ground source, we always encourage to use this, and you'll see later on why. You will have a delta T of 24.5 if the room temperature, for example, is 18. I'm looking at the bedroom there or landing or hall. So we use the EN442-1 that is a standard to measure radiator outputs and convectors in wet systems. That's what most manufacturers will use to determine these outputs. And also what radiator manufacturers provide to calculate the output of a radiator at various delta T's, we use what is called the correction factor. So most of the times we will get from every manufacturer an output of a delta T50, and we consider that as the standard, the benchmark, and to that then we'll apply the correction factor depending on the various flow and return temperatures that we've used and room temperature. So manufacturers provide what is called an exponent, N, and then we use a formula. So the correction factor is calculated using this formula is the delta T at which we want to find the new output divided by the delta T at the standard, a delta T at 50, and we put that at the power of n. And that's basically how this is calculated. This is a constant, and then that is typically 1.33 for standard panel rads and varies from 1.3 to 1.6 for convectors. Correction factors then for emitting sizing, depending on the type of application that we have, varies, as mentioned earlier, from 0.14 to 0.5. So higher the temperature, the bigger the correction factor will be. Again, different type of radiators in the market. You just have to make sure that if we try to reutilize existing radiators to be suitable at the new delta T, at the new flow and return temperature, that the model that we're going to use is, for example, we have cast iron radiators, which are becoming again very popular, in particular for one-off houses, where some end user have a preference for on the aesthetical side of these emitters. You want to make sure that they are used, cast iron in particular, with high temperature systems, because of their material on low temperature, they wouldn't perform as good. Having a look now at low temperature systems with heat pumps, underfloor heating, and radiators. If you're not familiar with a heat pump technology, heat pumps just use electrical power to do heating and cooling. Basically, you have just a small diagram here to show we have heat in on one side, on the evaporator side, where the refrigerant will go from liquid to gas. By the means of electrical power, we use a compressor, and this will then compress this gas, achieving higher temperatures. And on this side of things is where basically we transfer that energy from gas, from air, let's say, on this side to water. Therefore, the name air to water, or from ground source to water. Yeah. So typically, this is where we have a plate heat exchanger, and on one side we have the refrigerant gas, and on the other side we have the water side. And in this instance, the gas will condense and will go into a liquid form, go through an expansion valve, and the circuit goes over and over and over again, thousands of times. This is the principle really of any heat pump. If you look at it, for example, in cooling mode, this is where we take the heat and then we reject this outside. This is like your fridge, if you want. This is the one of the most common explanations that we can find out there, and everybody knows. I used to say this a lot in the past when I was doing CPDs on heat pumps, that people don't even know, but they have a heat pump in their home, and that is the fridge. So you'll see a lot of the older type that have it's a radiator at the back of it. You'll see that covered in dust and cobwebs at the back. You feel the heat coming off that. So heat pumps in heating mode are measured by their coefficient of performance at a specific outdoor temperature and flow temperature. Is very important when you're being given a COP on a heat pump to know at what conditions is that being given. Seasonal COP or SCOP is a calculated value, so all these are kind of lab tested values. And an SPF, or a seasonal performance factor, it's a measured value. So you will find that typically, depending on the way you operate a system, there is a variation between an SCOP and an SPF, because SPF is the actual real data, what has happened there. Ideally, and what want people really always to remember is that lower the flow temperature, the higher the COP, or the efficiency. Yeah. Again, lower the flow temperature, higher the COP. I have a little graph here just to show the dependence on the temperature, flow temperature, and COP. Obviously, the higher the temperature, because we need more power input, electrical power input, and we will get more thermal power output, the COP will be lower. So typically, for a low temperature radiator system, where we have temperatures around 40-45 degrees, you're looking at a seasonal COP around 4 And when we have on the floor heating systems around 30, 35 degrees, we're looking at a COP close to 5. When we produce domestic hot water, an average COP, SCOP, a seasonal COP for that will be 2.5 to 2.8. Because of the high efficiency that we can achieve at lower temperatures, the best suited system for a heat pump is an on-the-floor heating system. Typically, in particular for developments, and not only, you also have steel and aluminum radiator that are being used with this. But we have to remember that they have to be best designed at a lower flow temperature, typically around 40, 45 degrees, to to ensure that we're getting the best efficiency that we can out of the system. Same table that I was showing earlier. Now, just to give us in this instant our mean temperatures. So you will find that a lot of the times, for example, in a new home, people will be a little bit unsure about how to run or operate the system just because of the lower temperature in the radiator. It's always important if you deal with somebody new to this, just to let them know that to check their thermostat and see what the actual room temperature is, never mind the flow temperature or the temperature of the radiator. I have put in a nice slide that will show the ideal, let's say, heating scenario, typically, and the most comfortable way, where at about we achieve the best comfort at about 1.8 to 1.9 meters. And the underfloor heating system and the fact that a heat radiates from down up gives us the best comfort levels. There are other types of systems, obviously, the radiator being the most common one. You'll see that have a radiator on external wall. This is the kind of curve of heat, and then just slightly different than on the radiator placed on an internal wall. Ceiling heating is not too far off from that. So from these studies that were done before, we see that the optimal or the best heating system for our comfort in particular will be the underfloor heating systems. Probably a lot of you know, but if you don't, Romans used to use thermal water, so talking more than 2,000 years ago, and they used to have that put in their under their big villas and mansions, and they've been using underfloor heating more than 2,000 years ago. So it's well tested and proven. And ourselves here, we're in HEVAC and Polytherm, we've done this for more than 20 years. We'll be specialists in that. So it's definitely working. Let's put it that way. We have two types of underfloor heating systems, depending on what finish we put on top of the pipes. We have wet and dry. We have a profile panel type that is, as its name, it's a panel, it's a mat with dimples on it, in which you just put down the pipe in it. It's developed in Germany, and it's used in particular in for our projects for upstairs and in some retrofit scenarios. The most popular one is the clip rail, rapid rail system, where you'll have your subfloor insulation. On the insulation, you put your clip rail, and then you run the piping on it at different centers, depending the output you want to get out of it. And there is another type of system that we would use ourselves and supply. It's called a heat track panel, mainly used for retrofit scenarios. It's a plywood that has grooves in it, and then we use a 10 millimeter pipe that we put in this, and then you can put another sheet of plywood straight on top, and then you can finish straight with a carpet on tiling on top. Because there's no screed involved in this, we call it a dry system. This is a typical scenario, manifold that we use with all underfloor heating systems. You will have, if required or not, depending on the temperature, send out to manifold a mixing station. So we can, by the mixing valve here and the thermostatic head, you can control and set the temperature. And then you can pump directly through it, typically isolation valves with thermometers built in, so you can see temperature going out. You have your flow meters, and then you have actuators at the bottom. This is basically an actuator and a valve here, so acts like a little motorized valve controlling the individual loops, and then depending how much heat we want to put in a particular zone, we control the flow of water going there as well. Few things that are very important from the floor heating systems is the floor finish. It is the temperature, obviously, flow and return that we send in, design temperature, and the pipe spacing. Typically, this is done at 150 mil. These are all governed by EN 1264, and based on all of the above, we will get the heat output, watts per square meter, and the floor temperature that we will achieve in the room. Typically, you will not exceed 29 degrees at floor level to ensure that from a comfort point of view, it's not too hot, and also that we're not going to start to create convection and all dust and allergens to be brought into the air. Just another couple of examples now to show how the heat looks in an underfloor heating system. Very nice and very uniform distributed. And then to show how a radiator that is being in use for a while, for example, and hasn't been cleaned, you can have cold spots on that. Then if you will purge and clean this is most relevant for retrofit applications, where people are thinking to reutilize existing radiators. They all have to be properly double, triple flushed to make sure that if there's any sludge in them, that has been cleaned, because this will impact greatly on the heat output of that radiator. Another just example to see like a sectional radiator, cast iron or steel tube type of radiator, how and what output we get out of it. And this is another example just to show whether if it's cleaned or not, how it temperature that we can get out of a radiator. Controls are very important with all type of systems that we use. Typically, we use that to zone a system, as I mentioned earlier. The most common ones out there is an S-plan and a Y-plan. An S-plan will be a two-port motorized valve, one for heating, one for hot water. On heating, more than likely, we'll have an additional one, so we'll have typically 3 motorized valves. And a Y-plan, it typically uses a 3-port valve that just diverts between heating and hot water. We'll use them old-fashioned way on an on-off basis, so we're trying to move away from that. In particular, with low temperature technology, we want to let a heat pump run for as much as possible to get the most out of it. We can use thermostats, either set point, dial, or digital. We use programmable room thermostats to give us time and temperature control, depending on the application. We can have air probes or fluoroscreen probes. Like if you have a 230-volt system throughout the house, you'll not be allowed to put that into a bathroom. Therefore, you can put if you have on the floor heating, you can put a screed sensor, or you can put an air probe. Motorized valves are typically used, and then you look at more advanced controls via apps or centralized controls. Water compensating is very important. Typically, this is very rarely used with boilers in domestic applications, but all heat pumps out there will have that built in a standard. Just an example of thermostats that are being used at point with dial. It's very important to have a thermostat when you use with particular heat pump installations to ensure that the end user can see the temperature. Because you, as mentioned earlier, with radiators in particular, you can have a bit of a bad feedback that a radiator is lukewarm and the system is not working, where is actually the heating system and the heat pump and everything is working perfectly and the temperature is as it should be, but just it's a potential misunderstanding or lack of knowledge, or the system hasn't been handed over properly. You can have battery operated Wi-Fi, you know yourselves at the moment, there's so many type of solutions out there. They can all be integrated with these systems. You just need an enable to a motorized valve, as we have here, and the motorized valve will give us furthermore an enable signal to a heat pump or boiler, and then off you go. We can do heating and or hot water. Retrofit, it's obviously everybody's talking about retrofit and the issues that we may or we may not have, but it's very important that we have SR50 heat loss calculations done to ensure that the radiators are sized accordingly in a room-by-room scenario, so we can then determine the required heat pump output for the dwelling and for the radiators at various delta T's. I'm bringing this up again just to show you that it is important to keep that design temperature as low as possible to get as bigger efficiency as possible. Like, and SCOP of 4 means that for every unit of electricity consumed, you will generate extra 3. So if your cost per kilowatt hour is of electricity 20 cents, if you apply that efficiency, it actually costs you 5 cents to run that on a yearly basis. Now, I don't know what's going to happen over the next few months. It is, unfortunately, this price is just going to go up, but it still applies the same. And it is, in particular with gas, at the moment is very efficient to run a heat pump, and oil as well. In retrofit, more than likely, you'll have to replace your steel or aluminum radiators to ensure that these are meeting the required heat output per rooms. And just giving you an example here to see at a delta T, one of our hand rod radiators, a double 22 or double 600 height by 700 wide will give us roughly 1.2 kilowatts. And where the same radiator at a delta T of 22 will give us a third of that. And if we want to match the same output, more or less, the radiator is nearly, or it's actually over 3 times the size. So it's a 22,600 by 2.2 meters long. So it's very important then at an early stage to make all these calculations and to see if you actually have the space to fit one radiator, or you may have to fit 2 radiators depending on the type of retrofit. In sometimes in a kitchen dining small semi-D scenario, you may not be able to do that. You'll have to look at using vertical radiators and different other solutions, fan coils that will give a better outputs and so on. Talking about fan coils, this is kind of brings me towards the end of it. We're looking at trends in the heat emitting systems in dwellings in particular. We have heat emitters that can do both heating and cooling, and you can actually use underfloor heating for that. We just have to keep in mind that in particular for us here in Ireland, where we have a high humidity, if we are pumping chilled water into the floor, we can have dew forming on it, so it can get slippery. So for that reason, you require dew sensors, and then you have to limit the actual chilled water temperature that goes into an underfloor scenario. Fan coils are becoming more and more popular. They've been used for decades in commercial, office, hotel applications. We can use that in domestic as well. So they can do heating in the winter and cooling in the summer for us. As I mentioned earlier, most heat pumps have heating and cooling built in a standard. So you just have, to use a specific thermostat that can do both. We need to be able to enable the heat pump to know if it's doing heater or cooling. And that's all really. And as mentioned, the underfloor heating can be used to do that, but also a fan coil is used to do the same. You don't have to use fan coils throughout the house. You can put one per floor. You can get 2.5 kilowatts out of them. So if you have 2 of them, for example, even if your heating load is 10 kilowatts, you can get 10 kilowatt of cooling, but you may not have a 10 kilowatt cooling load that is more in a Mediterranean climate. is to keep in mind, though, that when we use fan coils, this requires separate power supply, because basically what we have in it, it's a fan, it's a little ventilator, yeah, that will just is forcing the air through a coil through which we're pumping either hot water or chilled water. They have their built-on controls, so they need power supply. And when we do cooling, because of the low temperature that we put through, we're going to have a good bit of condensate being formed. And for that reason, we have to make sure that we put in a condensate drainage. This is it. Thank you very much. And thanks again, Stephen and TUS, for this opportunity. And if we want to go to some questions, I hope I will have the right answers.
Thank you very much, Calin. That was brilliant. Very interesting in the parts on cooling as well. I think cooling is going to become a bigger and bigger issue in Ireland at the moment. But yeah, here's hoping for it. We have a question here from Mark. He's saying the heat track panel system for underfloor heating looks thin. Is there any insulation, he asks?
Typically what we do with that, because that is used in older Victorian kind of type houses, you will insulate in between the joists of the house, and then this is more or less screwed across that yeah. So as a dry system, that's the one. Profile panel is the one that has 11 or 30 mil high density insulation that can be just put down on an existing floor. Obviously, it doesn't give us the same U value, but it's better than having nothing underneath. So when you're height restricted, some applications, in some applications, it's very expensive to dig up a floor. So customers say, okay, we'll go with a lower level of insulation. Heat will more likely radiate up anyway. So I hope I answered the question there.
Yeah, that's perfect. We have another question coming in. Is like, does a heat pump come with or has a built-in hot water cylinder, or does it require special arrangement?
Heat pumps typically, depending on the type of heat pump out there. So if we're looking typically an air source heat pump, it's an outside unit. We call it an outdoor unit, in where the heat or the cooling is generated. But let's focus on the heat, and that then pumps that heat inside the house, either straight into your radiators or on the floor heating. And by the means of a 3-port valve, we will charge then a cylinder. In some applications, we have what we call an integrated or a compact unit. You have an outdoor unit, refrigerant split coming inside into this unit is like a fridge, and from there we go to do on the floor rads, and hot water is there, but it's not built in the outdoor unit.
That's perfect. We've a couple more questions coming through. We have there's a worry out there with homeowners around underfloor heating. Health issues are known to happen due to heat from floors as opposed to rads. Is this perhaps due to overheating underfloor circuits, they ask?
More than likely, yes. So if you'll have that, a lot of the systems out there potentially have been just lashed in, haven't been designed properly. This is where we see it as Polytherm as specialists. We do full proper calculations to the extent of we can go floor thickness and so on and so on. So yes, if you exceed a certain temperature at floor level, that will create discomfort, that will make dust and dust particles to rise. So like any other thing, if it's done incorrectly, you will not benefit from it. But more than likely, that's the cause. Too high temperature going into that screed, or to the screed is too thick. Yeah.
Perfect. Unfortunately, that's all we have time for. We have one more question, but again, I'll email it on to you, Calin, and hopefully you can get back to him.
Of course, no problem.
I'd like to thank everyone for joining us today, and I'd like to thank Calin for presenting today. And I hope you all can join us tomorrow when Keith Scully from Grant Engineering will be talking us through pipe sizing. So
thank you, Stephen, and thanks all you guys for joining us.
Thanks, Calin. Bye-bye.
All the best. Bye-bye.